Wait, I think we'll start now. Can one of you confirm if you can see my screen? Okay. So you've already covered the basics of buffer overflow previously. And what happens is that there's some functions like gets or scanf that they don't really count the number of bytes that are entered by a user. And so sometimes if it's a malicious user, they can sort of just write over everything in the stack and then write over the return address also. So one of the mitigation strategies to prevent such an overflow is the canary, basically. And what a canary is that if at any point there is an overflow that occurs and someone writes over the canary, somewhere right before the ret call, right before the stack is removed and whatever address is in the return address is loaded into EIP. Right before that, there is a function called stack check fail. So basically, if any of the bytes of the canary have been overwritten and they don't match with the original value, then there's a message printed called stack smashing detected, and it just exits. So it doesn't do a ret, it doesn't do a leave, it just exits entirely. Execution stops at that point. So basically, that's how canaries work. You place them somewhere in between a vulnerable buffer, whichever you think someone might try to overflow, and you place the canary between that and the return address. So if someone tries to override the return address, they would inevitably also override the canary. And then at the end, uh, execution is stopped because, and you get the error message stack smashing detected. Okay. Anyway, so that's okay. Here's a brief recap of what a buffer overflow is. You have the function gets. Gets doesn't check how many it doesn't check how many characters a user is inputting. It just inputs whatever and it writes into a buffer. So you can see here that before something's been written by the user, this particular memory cell, which isn't part of the buffer, has the hex value 48481. And then afterwards, after the user has written it over with a bunch of A's and a bunch of B's, you can see that it's overwritten by a bunch of B's. 42 is the ASCII code for the capital letter B. So you can see how it's very easy to write over the return address, make it point to a malicious function that gives the attacker control. So what happens with canaries is that you can see this first instruction here. There is something that's moving a quad word. So basically that's 64 bits into RAX, 64 bits or 8 bytes into RAX. And those 8 bytes are being pushed onto the stack at the location RBP -8. So it's been, so the stack basically looks like this. It has the return address, and then it has the old RBP saved. And that's where your base is pointing. That's where RBP points. It points to old RBP. And right over it, you're pushing some random value that some FS hex 28. I don't know. It's a random value basically. And towards the end, right before a ret call happens, there is a there is a compare function, not compare per se, but an XOR function. You guys might already know that what XOR does is if two uh, if two memory cells are exactly the same, the XOR of the result will be 0, like because every single bit is matching. So it compares the original value which was loaded into it to whatever is presently there at the location it was loaded into. So it checks the original value of the canary to whatever that was pushed onto the stack. Whatever is at RBP minus 8, it checks it. And if they are not equal, so if they're equal, it moves into this, it splits into this case. It does a leave and then it does a return. And if they're not equal and XOR does not return 0, it calls stack check fail. What that does is it just stops execution altogether. It does not return. Okay, so that's what's there on the slide. A random value is moved into racks and then it's pushed onto the stack. The same value is compared uh, to the quad word at the location it was pushed onto. If they are not equal, and that indicates an overflow, stack check field is called. Okay. So how can you bypass this security measure now that you know what it is? You have one option, which is to just guess the canary. Except on a 32-bit architecture, it might be possible to guess it. But on 64 bits, you can't really try 2 raised to 64 possible combinations for the canary. So it's close to impossible to brute force them or just guess them. The other option you have is to leak whatever value, whatever the canary is. And how exactly would you leak memory that's present on the stack? There's something called a format string vulnerability, and that's what's usually used to leak the value of the canary. And when you're doing a buffer, when you're overflowing again, now that you have the leaked value, you can rewrite the position of the canary with the same leaked value, and then you can rewrite the return address with whatever you want. So you can still perform an overflow exploit as long as you're able to leak the value of the canary. The general idea behind a format string is that there is a user controlled input string. So there's some function like scanf or gets that's asking you for an input, and then the same whatever you pass as input is probably going to be stored onto the stack somewhere, and the same variable is used as an argument to printf incorrectly. So there's something that the user is providing that's also used as the argument. Uh, I'll show you a small demonstration of printf. One second. Okay, so can one of you confirm if like letters are visible? Okay. Okay. So basically, in this function, in main you have a couple of local variables declared. The first one I've named user input, and it's basically the string %x%x. This is the format specifier for an integer. So this is what you would usually provide to printf so that um, if you provide %d, it decodes it as an unsigned integer, all of that stuff. A format specifier basically tells printf what the variable is. It tells it if it's a pointer to a string or if it's just an integer that's at that position. And printf always needs two arguments at the least. You need a format specifier and you need an argument that follows it so that it knows how to print that argument. Okay, so onto the stack, you have these four local variables. You have user input, which is a string that's just a bunch of %x. Then you have string 1, which is a few A's, string 2, which is a few B's, and string C, which is a few C's. Okay, and 1 second. I'll open another terminal so you can see what the output of this program would be. Okay, so the output of this program is as so. So in the first printf call, you see a bunch of %s's. This is basically the format specifier for a string. What it does is it passes the pointer to the start of the string. And then, okay, so printf sees this %s and then it sees the corresponding first argument, string 1, and it prints a bunch of A's. And then again, it's the same thing with the second format specifier. It looks at, it sees that it's a string format specifier, and then it decodes string to such that it's a string. So it's basically a pointer to wherever string 2 is being stored, and then it prints string 2. Same with the last one, format specifier followed by the string prints a bunch of C's. Okay, and in the next printf call, what I've done is there are 4 format specifiers. So there's 3 %s's, which suggests that the first 3 arguments are strings. And then there's also an extra %x that follows, %x that follows, but there's no corresponding argument to it. So what exactly would printf do? So printf is a vulnerable function. So for the first 3 arguments, it looks that it understands that it has to decode these into strings, and then it'll print a bunch of A's, and then a bunch of B's, and a bunch of C's. And then you see this random value 410 being printed. So what that is that printf is going to think that it just has to print the next argument that follows. So for a 32-bit system, what happens is that all the arguments are passed onto the stack. So printf just starts printing out values from the stack because it thinks those are its arguments. It just prints a random value that it thinks it's its argument. We'll go into what exactly this 410 is and where it is and all that. Okay, for the next printf call, you have 1 %x and you have 3 arguments that follow. There's no problem here. It just decodes the very first argument into a string and prints a bunch of A's. For the next one, I've given printf a single argument, which is the user input. And again, you can see user input is just defined as this constant string with 4 format specifiers. And likewise, you can see that printf has like printed 4 random values here. 2 zeros in between the 73 and then it just prints 4 values. We'll go into more detail about what these values are and where they came from. But this is basically a memory leak. Okay, and for the last one, I think I should go into GDB for this. 1 sec. Okay, so I'm hoping some of you still remember what a stack will look like. 1 second. Okay, so you can kind of see that there's place for the function's local variables below with the return address. But over the return I'm sorry, my bad. First, it pushes on a bunch of arguments to the function, and then the function is called. Maybe some of you might be familiar Okay, maybe I should just open GDB and show you. Okay, so the file for this is format. Okay, so the command disas main basically just gives you the assembly code for main. Okay. Um, okay, so we have about 6 printf calls. We want to understand what each of those are doing and how exactly all the arguments are pushed and what printf is printing. So before the first printf call here, you can see that the arguments to it are being passed. Uh, in a 64-bit system, basically all your arguments are passed using these registers. There's EDI, there's RSI, RCX, RDX. RAX is not used as such, but for some reason the compiler is first loading something into RAX and then loading that same thing into RSI. Okay, but basically, for a 64-bit system, you have all the arguments being passed by RDI, RSI, RCX, and RDX. There's also R8 and R9. We'll get to like which order these are called in and so. Okay, so basically you can see that EDI, which basically EDI carries the first argument. And for the first printf function, that first argument is basically this string, right? This string %x%x. It's just a string with format parameters. And since it's a constant string, it's stored in the read-only section of your memory for this executable. So you can see that into EDI, there is some address being moved. And that's in fact the address to the string %x %s to this string basically. That's your first argument. And then the second argument is a pointer to string 1 or just the location of string 1. The second argument is passed by RDX and then RCX and RAX. You can verify that this location RBP minus 15. RBP minus 15 was loaded into stack and it basically has a bunch of A's. You can see here that the string of A's, the ASCII code, the hex code for capital A is 41 in hex. So that value has been moved into racks and that has been pushed onto the stack, copied onto the stack at the location RBP minus 15. So basically your argument here, the argument that Rax is carrying is the capital A's. And then we can move on to RCX, RBP minus 27. That is carrying, again, you can see there's something that's been loaded into Rax and it's been copied at the location RBP minus 27. So 43 is capital C. So the location that's stored in RCX is the same as where this capital C string is located. And then in RDX, again, you can see um, it loads whatever is there at RBP minus 1E. And you can see again that this is a bunch of capital B's. 42 again is the ASCII code for capital B. So right before the printf call, you've seen how all the arguments to it have been loaded onto the stack. The format string is in EDI. All the arguments on the stack itself are in RCX, RDX, and RSI. And then printf is called and it prints, one second. Okay, so it just printed the corresponding strings based on whatever arguments that were passed to it. Okay, and for the second printf, what we see is that it's been given 4 format specifiers and only 3 arguments that follow it. Again, before this printf call, you can see these 3 arguments being loaded, the same strings at RBP minus 15, RBP minus 27, minus 1E. All of these strings are loaded. And EDI is again it holds the pointer to the format string. So it holds the pointer to %x, %s until %x. So that's what EDI holds. And then printf is called. One thing to note about 64-bit architectures is that you have RDI with the first argument, then RSI, then RDX, then RCX, and then R8 and R9. And then it starts, okay, so this is basically the calling convention for a 64-bit system. For any function, not just printf, the first argument will be passed by RDI or EDI, the second by RSI, the third with RDX, fourth with RCX, then R8 and R9. These are also registers. And then the remaining arguments are on stack. Okay, so again, since this printf has been given 4 format specifiers, it's going to try to print the next argument. And in this case, we've already used, for the second printf, we've already used RCX and RDX and RSI and EDI. The next register that'll hold an argument is R8. So what you see here, this 410, this is actually going to be the value that R8 holds, because that's the next argument according to the calling convention. To show you this on GDP, I'll have to, okay, so right before printf is called, you have to see what value R8 holds. And okay, so I'll set a breakpoint right before the second printf is called. And it hits the breakpoint, and the command IR, oh, my bad, I didn't run it. Okay, so it prints the first string. The first printf call is done. Now it hits a breakpoint before the second printf call. And okay, so the command IR is info registers. It basically just tells you what each of the registers are holding. And you can verify that R8 is holding the number 410. And as you continue, you see that the second printf call first printed whatever was being stored in RSI, then whatever was being stored in RDX, then whatever was being stored in RCX, and then as the last, since we had an extra format specifier and we didn't really give it an argument, it assumes that the next argument is an R8, and it prints whatever value was an R8. Okay, so continuing. Okay. Yeah, I can't do that. I'll set another breakpoint before. Okay, so on to the program again. I think the third printf's function is fairly clear. It just gets one format specifier, so it just prints the first argument. After that, you have the user input string. So if you look at the disassembly for this, I could just scroll up. Okay, that's the fourth printf. This is the first, second, third, and fourth. Okay, so the fourth printf, the only argument it's getting is RBP minus C. This is being loaded into RAX and then into RDI. And RDI is it's the register that gives you the first argument. So this fourth printf, it just has the one argument. But it has once it goes here, once it goes to the location of the string user input, it sees 4 function parameters, right? I mean, my bad. It sees 4 format specifiers. So once it sees this %x, it thinks, okay, I have to print the next argument, except we haven't given it another argument. So what it does is it naturally follows the calling convention. The next argument is usually passed by RSI. So it prints the value of RSI. Then it sees this second %s. The next function, the next argument is passed by RDX. So we'll print the value of RDX. And then it'll print RCX and then R8. Again, so you can kind of see how, suppose this user input was, so this is like the basis of what format string vulnerability is. Suppose you've given the user the freedom to give some sort of input, and they give you this input, and without using printf properly, you've just passed that user input as an argument. So what happens then is that uh, there's nothing stopping the user from giving a bunch of format specifiers as their input. And what happens then is basically a memory leak. For now, it's only leaking values of registers. Maybe that doesn't seem too important, but again, you'll remember that after the first 6 registers, all the other arguments are passed onto the stack itself. So by using this and by using enough format specifiers, the user might be able to get values on the stack that you don't really want them to have. Okay, so the fourth printf call, it just has the one argument in RDI, and then it gets called. And okay, I'll set a breakpoint right before it's called. Oh. Okay, so it now has 2 breakpoints, one after the second printf and one before the fourth printf. Okay, I've ignored the first breakpoint, and basically now I want to show you that the values it's printing are out of the registers itself. Again, our IR is info registers. It just lets you print out whatever values the registers hold. When I continue, this is the fourth printf call. It goes on to print the value 4052A0. And again, I'll remind you, the first argument is passed through RDI, which is the format parameter itself, the string. The second argument is passed by RSI. And RSI at this moment, before printf was called, holds 4052A0. And that's what printf has printed here. Then then it leaks the value of RDX and RCX, both of which hold 0, and it's printed 2 zeros. And finally, it also prints the value R8. R8 holds the value of 73. So that's what you see it printing over here. Okay, so on to the last printf call. Okay, so one more thing you might have noticed is that um, this format specifier %x, it uh, it tries to interpret whatever argument as an integer, and integers are only 4 bytes long. So instead of printing the entire memory cell, you'll notice that this printf and the second printf, they only print the lower 4 bytes and they ignore the top 4 because they've been told to treat it as an integer. But when you're trying to leak memory, when you're trying to leak canaries at least, they're 8 bytes long, so you can't really use %x because it'll only leak 4 bytes. And then the internal pointer of printf will just move on to the next memory cell and leave the other part of the canary unread. So instead of using %x, we use the format specifier %lx or a long int. So this will leak the entire memory address. I mean, it'll leak the entire memory cell. It'll leak 8 bytes. You can either use this or %p also leaks 8 bytes. Okay, so on to the very last printf. Um, the sixth printf. Okay, so it's just this. Again, you see that it's been passed only one argument, and that one argument is this long string of %lx, lx, lx. So what this does is this whole string is first stored into EDI, and that's your first argument. The next 5 arguments, again, they're stored by RSI, then RDX, RCX, R8, and R9. So this will give you the value of RSI. The next one will give you the value of RDX. The next one will give you RCX, R8, R9. So far, nothing important. And then these last 2 %lx, they'll start leaking the stack values. So to see this in play, I'll place a breakpoint right before the last printf is called. Okay, and then I'll run this. It hit the breakpoint at main, in main, like right before the last printf is called. This is probably uninteresting to you as of now because we've been over this already. We know that it'll print the values of RCX, RDX, R8, and R9. But okay, so this command basically prints 40 memory cells after RSP. So it prints the first 40 elements of the stack. Now something interesting happens when printf is called. Again, these first 5 values. Is that 5? Okay. So these 5 values are basically again our SI, followed by RDX, and then RCX. After RCX, there's R8 and R9, which are 78 and 0. So, okay, it printed these first 5 values of a register. We know this already. They're not particularly useful yet. and then it starts printing these numbers. Again, you might remember that we passed a bunch of C's into the stack because it's a local variable. String 3 is a local variable, so it's been stored on the stack. And you'll see that the value that printf ends up printing is a bunch of 43s. It's a bunch of C's. So what memory cell is it printing? First, it prints 0. It's printing the very first element on RSP. It printed this memory cell. Okay, again, since I'm on 64-bit, it's going to print by one memory cell, I mean 8 bytes. And every 2 characters you see, that's 1 byte. So this is 1 byte. The next 2 are another byte. So this whole thing is 8 bytes. It prints the first memory cell, and that just holds the value 0. Then it goes on to print this. Another thing you might notice is that it's printed them in sort of the opposite way. But okay, so it prints 43 first, then another 43, then another, and then it prints 0 in the end. So the way the string is being read is from this memory cell first and then this. Anyway, now you know that this format string is capable of leaking values that are on the stack. And that's a hint to how you might start leaking canary values. Okay, so okay, so you understood what exactly the format string vulnerability is. First, if you have a function printf and it's been used correctly, as in there is one format specifier and there is a variable, there's an argument that follows corresponding to it, printf will know what to do and which argument to print. But if you don't give it you don't give it the right amount of format specifiers, it might malfunction and leak addresses. So in this example, this is the incorrect usage of printf. You've only given it a string, but you haven't told it that it has to decipher it as a string or anything. And if this local variable name is something that the user is inputting, then there's nothing that we as users are not allowed to do. We can give the parameters %x or %s, and you've seen how printf decodes those. Okay. Can everyone still hear me? Okay, so again, you can see the different the table here that okay the table here that tells you which format specifier is for what. %d for decimal, %x for hexadecimal but unsigned. Then if you add L before this, it basically it's a modifier and it's a long int. So it'll print out 8 bytes instead of 4 for a regular integer. Okay, now on to a 32-bit system. Suppose there is something on the buffer, the user input, and the user has given you this input. He has given you some memory address followed by %x, a few format specifiers. So onto the stack, all of this stuff is stored. So the stack has this memory address first, and then %x, and then %s in the end. Now printf, if it gets, oh, this is the case for this second case where printf is just getting one argument and nothing else. So printf is going to go to that argument. The first argument it gets is the address of this buffer. So it goes to the address. It sees this %x, and it thinks that it has to it has to give you an integer value somehow. So it'll start printing values that it considers its arguments, and usually all the arguments are passed over the function frame. Like as in all the arguments are passed and then the function is called. So printf is going to assume that this cell that the yellow arrow is pointing to, that's the argument corresponding to the first %x, and it'll start printing that value from the stack. Again, similarly, it's going to start it'll start printing all of these memory cells corresponding to the different x's. For the second one, it'll print this memory cell, the second one, and then it hits %s. %s is basically how it functions is it gives you the pointer to a string, and then it prints the string based on that. So if this is a valid address, then printf will go to that address and print out whatever value is there. Okay, and this is just the case for 32-bit architectures. You'll remember that all the arguments are pushed onto the stack. So 32-bit does not use registers to pass arguments to its functions. So printf receives the first argument, which is the format parameters that the user inputted. So since that's the string, printf basically receives the address of this buffer. Then it reads the first x and naively looks for arguments pushed onto the stack right over it, and it starts printing the memory cells, interpreting them as unsigned integers because %x. Okay, for a 64-bit architecture, like we've just covered, you can see here. You can see here that the calling convention, the first 6 arguments are passed by registers, and the remaining arguments are passed onto the stack itself. So with enough format specifiers, you will print all of these registers first. Again, you can verify that this is the register value of RSI, and then it starts printing stack values. So that's what the format string vulnerability is, the key differences between 32-bit and 64. Next up, you have positional arguments. Suppose the programmer, they gave you a read function. It seems as if you want a lot of values to be printed, you have to give it a lot of format specifiers. But that might be limited by how big your buffer is. Suppose it's not scanf that took the input of the buffer. Suppose it was some other function like read. Read basically also considers how many characters it can store in a buffer. So there you might give it a very, very long input. You might give it a lot of format specifiers, but only a few of it only some of it is stored onto the stack. And yeah, so you need a way to get to positions on the stack that won't be covered by every single format specifier. You have something called a positional argument. This basically picks which argument you have to pick, which argument printf has to print. So in the example here, you have $1C. So it basically tells printf to look at the first argument and print that. So whatever the value of n is, printf is going to print that numbered argument, I guess. Okay. So here again, the last printf is sort of a good example. The first $3 is going to tell printf to look at the third argument, and in this case, that's the character C. And then the second format parameter, it has $2, so it'll tell printf to look at the second argument, which is the character B. So first it prints C, then B, then A. So using this positional argument, you're able to pick which argument you wanted to print. Okay, so now that we have this, we already have a way of leaking memory addresses from the stack. Now we also have something that gives us control over exactly which memory address to leak. So once you find out what n is, you can just pass on to printf this argument, %n $lx, and it'll print out exactly that argument. Okay, so how do you locate and leak canaries? You on Linux, basically canaries always end with 00. This is meant for some functions that printf terminates anytime it hits a null byte. So canaries end with 00 because that's where you want printf to stop. Okay, so canaries on Linux usually end with 00, and they change every single time you run the program. I think I might have forgotten that point. So right, this random value that's pushed onto the stack, it can't be the same because it can't be the same with every execution, because then you will just find the value once and um, that'll be it. You can just write over to that value. So it has to change every time you execute the binary. Okay, so the fact that it ends in 00 and changes every time you run the program makes it harder to brute force. Obviously, you can't guess it. You can't read it once and then write over the same value you read once in the next execution. But it also makes it somewhat easy to spot. So if I print a bunch of memory cells from the stack, I'll see something ending in 00, and it keeps changing every time I run the program again. And that's how you spot your canary. There are methods of automating this process so that you don't have to use GDB and look at memory cells yourself. But as of now, we won't go into that. Okay, so you can leak a canary if there's some unsanitized input being printed. So basically, if there's a format string vulnerabilities. So here again, you can see that buffer is a user input, and then printf is being called the wrong way. It's been given just the one input that's from the user. So it's able to um, print and leak some values for us. Okay, so we'll do one example of exactly how you can do all of this, how you can leak and find canaries. Okay, so this is a function. This is the source code for the function. It's not complete, as in you don't have the code for the canary being shown here. But basically, what it does is these first few parameters, the first few functions, they print welcome to the time machine. And then they are giving you the location of some function. In the previous session, you would have already covered what red to win is. And you see that the pointer they're giving you, the address they're giving you, is the address of this function, take me to the future. That's your equivalent to win function. So if you can change the return address to whatever this code is giving you, then you'll get your flag. You'll change execution flow basically. Okay, so and then on to local variables, you have the string with a bunch of format specifiers. Then you have 3 integers that are initialized to 0. Then you have a character buffer. Okay, so first it's called here, and this character buffer it's called, and you get the prompt, what in the good world is your name? And then you see scanf. Again, this is vulnerable to overflow. You can give buffer. You don't have to give it exactly 20 bytes. You can give it something else. What year do you want to go to? And it stores that into the integer year. What month? It stores that into the integer month. And lastly, into the integer day. And then in the end, you'll notice it says taking percent %s2 and comma buffer. Um, so, oh, no, that's not. 1 second. Yeah, so the second printf here that says format, comma, date, month, year. This is going to take the argument format, which is already defined in here. It'll take this string person with 3 integer format specifiers. And then according to all of those, it's going to print date, month, and year and replace it with that. But this, as you'll see, it's taking in, if you can overwrite the buffer and you can give it a bunch of format specifiers, then you might be able to leak some addresses. Oh, and then again, in the end, you have a scanf, which again you can overflow. So the basic logic to solve a challenge with canaries in it is first you have to find how to leak a canary. So you'll do that by overflowing you'll do that by using the format string vulnerability. You'll overflow something the user input and you'll give it a bunch of format specifiers that will start leaking some values. And then there's some printf call that gives you back the leaked values. And then after that, once you have the canary value, you will write back into the buffer. You'll rewrite the same value of the canary where it's supposed to be. And that's all. And you'll rewrite the return address to your win function. And that's how you break this. So, so let's see how this thing is run. Okay, it's asking me for my name. I can give it a bunch of anything else I might do for you. And okay, so you can see that it prints the string and then it prints the corresponding integers to that format string. Okay, so now on to GDB. Okay. So again, you can look at what exactly a canary is. In the beginning, there's some value that's being moved into RBP -8, right? And that's your canary value. And in the end, there's a function that compares this value, the same original value, to whatever is presently at RBP -8. So if someone has overflown into this, this compare is going to give you a jump if not equal, and then so compare will return that these two are not equal, and the flow will jump to main plus 454. So it calls stack check fail local. So let's just see what happens if I overwrite, if I give it a lot of, if I give it a very long input, and I'm hoping this overrides the canary. It throws the error message stack smashing detected, terminated. Okay, so back to GDB. So my goal is to see how exactly I can print values. So firstly, I'm going to set a breakpoint right after the canary is loaded into REX, because I want to make sure that whatever I'm printing is the canary itself. So I'll set a breakpoint there. And then after my very first scanf, after your first scanf, after you've written into the buffer named buffer, after the first scanf, you can see, you can see whatever this, okay, one second. After the first printf, my bad. No, I'll just set a breakpoint at both places, I guess. So I set this one after scanf, and then I'm going to set another breakpoint right after, one sec. Okay, so right after this printf that says taking percent %s2 something, I will set another breakpoint to see exactly what has been printed. Okay. So wait, that's which printf is that? This is the first scanf, and then it's the fifth printf. So I look for where that is. Wait. Okay, so it's this printf. So right after this printf has been called, again I lost it. Okay. Okay, so right after that printf, I'm hoping it's the fifth one. I can set another breakpoint. Okay, so, and then I'll run this program. We hit the very first breakpoint, and you'll remember that was the breakpoint we set right after the canary was loaded into RAX. So here, if I type in info registers, I'll see that REX holds the value of the canary. And then as I continue, I can give this a very long string followed by, this is just a random guess. Okay. So we hit the second breakpoint, and now at this point I can print out the first. Okay, so this command again, it prints out the first 40 memory cells of, I hope I didn't overwrite canary. Okay, I didn't. Okay, so it prints out the first 40 memory cells of the stack. And then the next command I will give it is, okay, so examine and then following 10 memory cells after RBP. So it will print out the 10 memory cells following RBP after, yeah, it just prints all the values after RBP, and this one prints all the values after RSP. And you'll notice that RBP is pointing to some location ending in F00. And okay, so since RBP points to its to old RBP, this is basically your old RBP, and the value that's right over it is the return address. So this is what we're aiming to overwrite with this address. This address that says the future lies at something. We want the return address to be changed to that. So okay, so this is where this is what we want to overwrite. Again, you'll notice that RAX holds some value starting with F205 and then it ends in 00. This is your canary value. Your task is to spot where that is on the stack. Again, we already know from the assembly that this value, this random value that was in RAX, was moved to RBP -8. So it's present right over RBP. So we spot where the RBP is over here on the stack. This is where the RBP is. This is old RBP, and this is the return address that we're trying to modify. And this is the canary value. It's right over RBP. So it starts with F2, what was it? F2059C, and then B3, and then it ends in 00. So this is where your canary is. And since our first buffer, we've passed a bunch of capital A's followed by $10P. So we just have to spot where this whole string of capital A's is. Again, I'll remind you that the ASCII code for capital A is 41. So from that, we can spot that this is where all the numbers, this is where the string is, right? And now if I want to calculate how far away the canary is from the start of the buffer, because when I'm going to overwrite it, I will be overwriting it using the same character array, the same buffer. So you have to know what the offset from the start of the buffer is to wherever the canary is. And that's all this part, this whole part. Again, I'll remind you that every 2 characters, so the 41 that's been highlighted, that's 1 byte. So this whole thing is 4 bytes and this entire memory cell is 8 bytes. This whole thing will be 16 bytes, then 32, then 48, and plus 8, so 56. So after I've overwritten these 56, my task is basically to write whatever I want in these 56 bytes. And then after that, I have to rewrite the value of the canary with this value itself. And then I have to give 8 bytes to overwrite the old RBP. And then this is my return address, which I have to overwrite with the address of this function. Okay, so continuing. Oh, my bad. What was this for? Not necessary, I guess. So we haven't sufficiently overflown the buffer, so it's not really printing any memory addresses yet. So we'll try giving it a longer string. So we'll run that again. Again, this is our canary. It's changed its value from last time. It's still ending in 00. After that, oh, no. Continue. What in the good world is your name? So I basically just guess and check and see what values are being oh, I was supposed to. Okay, so it printed out some value for me when I gave it this huge string followed by 10 and followed by the positional argument and then $P. So it printed out some value 493. We just have to find the offset of this value, this address that it printed out, to the canary, and then we can just modify this number to make it point whatever argument, to make it print whatever argument we want it to print. So, okay, 1 second. I was supposed to, again, this is your canary value. Again, it's changed and it still ends in 00. Okay, so I'm going to give it the same string. It hit a breakpoint. Okay, so at this point, I'll start printing 40 values after RSP. Again, we can see that the canary has not been overwritten. Has it? Hope not. No. Okay. What year do you want to go to? Keep doing this. Okay. Yeah. Okay, so it printed out this memory address, the same as we saw last time. We want to see where this is in relation to the canary. So you go to the stack and you try to spot. Okay, so got it. It's 493100. That's this memory cell right here, right? Okay, and after that, you see that the canary is somewhere here. So if this is where the number 10 got you, then this will be the 11th argument. This will be the 12th, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, wait, did I overcount? Okay, so this is 10. Okay, so this is the 20th argument, and your canary is the 21st argument. Okay, so we just have to, once we modify this initial input of ours from 10 to 21, we will be able to get printf to print the canary value itself. So I'll run this again. Oh, shit. Why does it keep moving to the next one? I'll just okay, so I'll just comment this somewhere. I'll try printing it again. Okay, I'll set 1 again after where RAX was. And 1 after the printf that prints the address out, the 5th one. Okay, so the value in RAX, again, it's the canary. Okay, so I want to give this the string. And modify the 10 to 21. Oh, that was my bad. I don't think it's the 5th printf. Either way, I think we should. Okay, so we see here that this long string has given us a bunch of A's, followed by this, which is the canary we wanted. Um, and that's pretty much all that we needed. We needed printf to give us the canary value so that we can automate the whole process. We don't really have to use GDB and copy values. We can just get printf to leak the value of the canary. And we found that this extremely long string is giving us the value of the canary. And now onto the exploit. Okay, so I'll briefly explain what the exploit is doing. It's okay if you don't understand it. Quite complicated. So first you import the Poon tools library, and then you start running the binary. The name of it is say hello. Okay, so this line, recv until receive until, it'll basically receive everything since there's no user input required before this line. It just receives everything that all printfs give out until this string is hit. What in the good name is your name, dear? So it stops here. And then after this, it sends us, we have to send that really long string followed by 21 and then the pointer format specifier, right? So after we do that, again, it asks us for a bunch of inputs. It asks us for the year, and then we receive until there, and then we send line. We send whatever we send our inputs through this function, basically, and then the month, same with the day, and then finally, printf receives taking some really. It prints out the canary, right? So we want it to receive until this string, followed by the dot, and then whatever follows it is the canary value. So you want it to receive until this, and then the next value you receive is going to be the canary itself. So that's what the leaked value, you're receiving it and then you're stripping it. So what this function strip does is it removes the new line character. So if the canary is, since it's being printed to your screen as a string, you have to remove whatever blank spaces and new lines you might have after the canary that the receive line will receive. So that's what strip does. And then after that, we have the canary value. You're turning it into an integer from a string. And after that, ideally, while you're rewriting canaries back into its original location, it's a huge pain to uh, think about endianness and write it. You have to write the bytes in the the opposite order, all of that stuff. But because you've imported the library, there is a function that basically converts whatever integer value into the address format, and now you can just directly use this converted value in your payload. Okay, so again, you probably remember that the offset from the start of the buffer till where the canary was 56 bytes we counted. And then the return address is basically what you want to overwrite into the return address. Again, you've used the P64 function to convert it into an address, basically. And then to overwrite the RBP. So what we had was we had the canary, and then we had the old RBP, and then we had the return. You overwrote everything till you overwrote 56 bytes till you got to the canary. That's your padding, and it's just capital A and 56 of those. And then you found the canary that we leaked using the format vulnerability. That's the next thing you have to overwrite. And then into RBP, we're again overwriting 8 junk bytes, which is overwriting 8 capital A's. And then lastly, we want to send it the return address. We want to write the return address of the win function. So that's what this whole, so it sends this payload and then it receives whatever happens after that. We'll look at what that is. Okay, so to run this exploit, so basically what it did is it started the binary, it ran the binary, and then it prints triggered successfully. So if you look at the source code again, triggered successfully means that void take me to the future was called. So basically means that we were able to overwrite the return address. And that's all there is to this exploit. Okay, we still have like half an hour left. So if any of you have doubts, please raise your hands and I'll unmute you and you can ask. Or I could do a rough summary of everything we covered today. Anyone? Anyone can raise their hands. Okay, should I assume that there's no doubts at all?
Yeah, I can take a quick summary.
Okay. Sanjay Sutar, 1 second. I'll unmute you. Yeah, you can speak now.
Hello.
Yeah. What's your question?
If I don't understand anything.
You don't understand anything, or is that a
Yes.
specific doubt?
No,
Okay,
if I
so
understand.
I'll do a brief I'll do a brief like summary anyway, so I think you'll be able to understand.
Okay.
Okay. Okay, so we'll just do a brief summary then. Okay, so we started off with exactly what a buffer overflow is. Uh, if there's a if you use functions like gets or scanf, you're able to override into buffers and you're able to override the return address itself, right? And after that, so you want some sort of security measure that prevents return addresses from being overwritten because you don't want you want the program execution to go the way it was supposed to, not the way some malicious user might want it to. So basically, what you do is between your vulnerable buffer, which is a local variable, and between your return address, which you don't want to be overwritten, you insert something called a canary. What happens? So, what exactly a canary does is that in the beginning there's some random value that's being loaded into some location between the return address and the buffer itself. And in the end, it's being compared, and there is a check that happens to see if the canary is still the same or it has changed somehow during whatever happened. So if the canary has been changed, it indicates that someone tried to overflow a buffer, right? So obviously you don't want that to happen. And what happens when the canary is different from what it began with is that there's a function called stack check fail that's called. And once that's called, it doesn't return, it just exits. So nothing can be done. You can't override the return address because it just stopped executing altogether. But if the canary is the same as it was initially, then you go to this and then you do the leave and the return. So it seems almost like the perfect strategy to prevent buffer overflow because there's no way someone's going to guess 64 bits and get it right because that's a lot of possibilities. That's 2 raised to 64 possibilities, right? So it's close to impossible to just guess what the canary value is. You'll probably get a few bytes wrong, and then execution will stop because stack check fail is called, right? But if there is a way of leaking memory addresses while you're still executing whatever the executable, and that's due to a vulnerability called the format string vulnerability. Basically, what that is if you don't provide format specifiers properly, then printf will just start printing whatever its arguments are, right? And on 32-bit systems, the arguments are basically stuff that was passed on to the stack itself. Like you might have noticed that RDI and RSI, I mean EDI and ESI are pushed onto the stack. The first will hold the format string, and the second will hold the location of the variable that needs to be printed. So for 32-bit printf, if you don't use it correctly and you don't give it enough format specifiers, it'll just start printing whatever values are on the stack because those are its arguments, right? For 64-bit, it's slightly different, as in the arguments are also passed using registers. The first 6 arguments are passed. This picture is right out of Wikipedia, the calling conventions for 64-bit, and you can see this is for Linux systems. Okay, so the first 6 arguments are passed using RDI, RSI, RDX, RCX, R8, and R9. And then the next, if there's more than 6 arguments, those arguments are just pushed onto the stack, just like how it is with 32-bit. So what printf does, if it's used incorrectly, is that it'll start printing the values of these registers first. RDI, RSI, RDX, all of those. And then it'll start printing values from the stack. So far, okay, hopefully. Then you have something called...
Excuse me.
Oh,
Are you
I
screen
am not
sharing or
sharing.
you're...
Nope. I forgot entirely. 1 second. Okay. So again, I'll just start where I left off. This picture took it right out of Wikipedia. This is the calling convention for 64-bit. So the first 6 arguments are passed using the registers, and then whatever arguments are following it are pushed onto the stack itself. So when you tell printf to start printing arguments and you've not really given it a format specifier, it'll start printing the values of these registers. It'll start printing the value of RSI, RDX, RCX, all of these. And then it'll start printing values on the stack because that's where it thinks all its arguments are. So this is something called the positional argument. Suppose for some reason the string that the user is allowed to input is it's being taken by some function like read. That counts the number of characters the user is inputting, and if it exceeds the limit, it just doesn't store those onto the stack. So unlike with scanf, you will be limited by how big of a string, how big of an input you can give. So you can't just type, you can't give it a very lengthy string and just type like 100 of these %lx to leak 100 values, because it simply won't store that string. It'll just store a part of it. So instead of that, as attackers, you would use something called positional argument. So in printf, normally I would just give it, if I give it the %c, the %c format specifier, it'll just print the very first argument. But if I want to select the first, second, or third, and I wanted to print specifically those arguments, then I would add the $. So this basically tells printf which argument to print. And you combine that with a format vulnerability. Suppose I don't want printf to print RSI and all these registers, and I wanted to start printing the stack values, and I don't really want it to print A's or B's that I gave as input. I want it to print out the canary value. What I could do is, what's usually done is you see, for a random string, you see what is being printed out, right? Like in the example, we saw that there was a random memory cell being printed out. And then we looked at which memory cell was being printed out. And then we looked at how far away it is from the canary, so that we can determine this number n. So once you determine n, you're able to get printf to print the canary for you. And yeah, you'll just write that into your exploit. Again, as a review of everything, what is a canary? It's just some random value that's loaded and pushed onto the stack. Here you can see it's being loaded into RAX, and then it's being stored at the location RBP -8. So after you do this, you can set a breakpoint right after the first scanf, and then you can give it a bunch of A's, and then you can print out the values on the stack using the examine function of GDB, and then you can see where exactly your input has been given, right? So once you see where the start of the buffer is, you can locate it using all the capital A's. Then you can see where the canary is relative to the start of the buffer. And then you can figure out what the padding will be, right? After that, the next thing we need is, after we found the padding, we need the canary itself. So to get the canary itself, again, we use the format string vulnerability combined with this positional argument. First, we just gave it a bunch of A's and we gave it some random number argument. And it printed some random value on the stack. You can see where that random value is in relation to the canary. And you can see what new number you should give so that it stops printing the initial value and it starts printing the canary. So you basically calculate the offset between the value that you print first, and then you use it to figure out what input to give so that printf is going to print out the value of the canary. And after that, you have your canary too, you have your return address too. And again, as discussed, these first 56 A's, they're to override the space between the start of the buffer to the canary. Then you write the canary into itself. And then you give 8 A's because you're trying to overwrite the old RBP. And then you give it the return address. So that's all you have to do. And there was a Python code for this. And yeah, that's about it. There's also like this is an alternative method of doing things if you don't really want to count how many bytes to give it. You can use something called a De Bruijn sequence. The simplest way I can explain it is, say you have the 4-digit string 1100. Okay, wait. Maybe I should use a board for this. Or, no, maybe you guys can remember 1100. So what a De Bruijn sequence is that every single segment of it, every single subsequence of it is going to be unique. So basically, if you look at this really long string, 4 A's in the start, B's and a bunch of A's and a bunch of, and say that whatever location you're overflowing it into is an 8-byte location. What should be the case is that if you take any consecutive 8 characters, those will be unique from any other subsequence you can choose. So in the example 1100, say that whatever location I'm overflowing is just 2 bits. After overflowing, if the location contains the numbers 11, then I know that it starts wherever the start of my string is, because my original string was 1100. Um, if it contains the string 10, then I know that it starts at the second character of my string, and then it ends at the third character. So basically, based on what numbers that get written into this location of yours, you can figure out the distance from the start of the buffer. So you don't really have to use GDB and go through all that counting the bytes and all that. You can just use this is there's a function in Radar 2 that basically has this inbuilt. Radar 2 is like it's like GDB on steroids. So it has a bunch of tools that make exploiting easier. So it can generate a very long non-repeating pattern, and you can use that to locate offsets. It does all of this on its own with just a few instructions. So it's quite useful to have. But otherwise, if you prefer GDB and like looking at what exactly is happening, then you can just start printing values of a stack and calculate offsets yourself. Okay, so that's about it for the session. Okay, Sanjay, Sutar, I think you can unmute yourself, right? You can unmute and speak. Okay. Are there any doubts? I'm going to take that as a no, and that's it for today's session. Sanjay, if you still have doubts, I think you should watch the recording ones, and I can give you a bunch of links to where you can read more about more about the format string vulnerability, more about what canaries are and all that. You can, mic is allowed. You can speak if you want to. Sanjay? Okay. You guys can leave if you want to. We're done for today.
Yeah, I think that's it. Can end the meeting.
Okay.